All right, so the first one to get down here is exposure, okay? They're going to use some technical words here, but I'll break it down and make it understandable. Exposure is defined by is narrowly defined as the intensity of radiation incident upon the surface of an object. So this is not radiation that has entered the body. We want to measure exposure. We want to know how much could you absorb. How much radiation could be absorbed into you. So we measure it at the surface. In fact, we measure it just a bit above the surface of the body. In fact, it's easiest to measure the intensity in the air above the surface of the body. And the way that's done, you guys know already, right? X-rays, as well as other types of particulate radiation, alpha and beta and gamma, which is also electromagnetic, but importantly, alpha, beta, gamma, and X radiation, all those types of radiation that are what are considered ionizing, they can create charged particles. They can charge the air in the room, okay? They can do that by, as you guys hopefully already know, removing electrons from atoms in molecules, okay? Molecules of air, right? Air is oxygen, it's nitrogen, it's CO2, it's argon, it's a bunch of other noble gases. But importantly, X-rays, gamma rays, alpha and beta particles, they can ionize matter. So they can ionize the air in the room, and we can measure the amount of charge created in the air in the room, in an area. Okay, so we can measure radiation exposure because of that. So we're going to call that entrance skin exposure, or ESE. And it is simply the intensity of radiation entering through the surface of the body, not necessarily the amount absorbed by the body. Why isn't it measuring how much radiation will be absorbed by the body? Why can't we know how much is going to be absorbed based on how much it can enter the body? So why can't we know based on what the exposure above the skin is? So we get the exposure above the skin, right? An inch above the skin in the air. If we know how much that is, why can't we know how much will be absorbed by the body? Different body types. So think like tissue thicknesses and densities, right? Me versus one of you smaller students, right? I'm going to absorb more, right, than a smaller student, right? A thicker body part will absorb more. And along those same lines, a denser body part will absorb more, right? So if you measured in X-ray terms, if we measured the remnant beam energy, right, the amount of radiation in the remnant beam, that's significantly less than what entered the body, right? But what's going to be in the remnant beam, how much radiation's in the remnant beam, is going to be very different from patient to patient, from body thickness to body thickness. Okay, so just because we can know what the entrance skin exposure is, we can't necessarily know what the actual absorbed dose will be. Okay, so absorbed dose is going to be a different measurement. Okay. So entrance skin exposure is its own thing, okay? All right, so yeah, exposure. You are exposed to things from the outside of you, right? If it's inside of you, you're not exposed to it. It's part of you, or it's been absorbed into you, right? So that's what we mean by exposure, is exposure from outside the body, okay? So radiation exposure, again, narrowly defined as the intensity of radiation incident upon the surface of a body. By the way, we're going to use that word incident a lot. The incident radiation is let's say the first radiation to interact with matter. If we're talking about single particle interactions, the incident particle is the one that started the interaction. Okay, the first one to hit something. And yeah, the only way to count X-ray photons before they are absorbed by the object is to measure them in the air above the object. While the air interacts with things like the X-ray beam and interacts with things like particulate radiation, the air in the room doesn't markedly absorb anything, right? Whatever, in atomic terms, the air in the room is no different than you, right? The air in the room is matter. It's just matter that's a gas, right? Versus you as a matter that is a liquid and a solid and some gases too, okay? It's just atoms though, okay? But importantly, because the air is in gaseous form and it's not so dense, right? The X-ray beam isn't, as I said, isn't noticeably absorbed by the air in the room. So we can measure the amount of radiation in the air and infer from that how much will the body be exposed to. Okay. So yeah, in the air, there are atoms of oxygen and atoms of nitrogen, most principally, but other smaller amounts of other elements as well. But importantly, those atoms have electrons in orbit, and the ionizing radiation that we use, X-rays and other types of ionizing radiation, gamma, beta, alpha, can ionize that air. They can remove electrons from the air molecules, and if you put a detection device in that area, the atoms in that detection device will detect the ionized particles. It can detect those ionized particles, and it can generate a small amount of electric current. That electric current is proportional to the amount of radiation, and so we can measure the electric current and infer the amount of radiation in the air in the room. Okay, so here's the actual unit that we use. The unit for exposure is called the coulomb per kilogram. A coulomb is just an amount of electric charge. In fact, it is equivalent to 6 billion ionization events in a cubic meter. So here's a number to remember. 1 coulomb per kilogram is equal to, or is, 6.3 times 10 to the 18th ionizations in 1 cubic meter of air. If you ionize that many atoms in a cubic meter of air, that's called 1 coulomb per kilogram. A coulomb is an amount of electric charge. 6 billion ionization events, that's an amount of charge. Okay. A cubic meter is just a cubic meter. So 1 meter cubed. They actually show the meter cubed on the screen there. Why is a cubic meter referred to as a kilogram of air? Because if you could box up 1 cubic meter of air and put it on a scale, it weighs 1 kilogram. Those of us who might not be so adept at understanding metric units yet, maybe those of us that are can tell the rest of us what is a kilogram in like standard units that you would be used to. 2.2? 2.2 what? Pounds, good. So you guys know what pounds are, right? If you don't know what a kilogram is, 1 kilogram is equal to 2.2 pounds. So 1 cubic meter of air weighs 2.2 pounds. So roughly the size of your tabletop area, okay? But, you know, a meter by a meter by a meter, 1 cubic meter. And at regular atmospheric pressure, so like regular like sea level pressure, right? You may know that air thins out the higher up you go in altitude, okay? So at roughly typical atmospheric pressure, a cubic meter of air weighs 1 kilogram. Okay. So that's our unit for exposure. We measure it in coulombs per kilogram. Okay. So then we come to this unit, air kerma. I gave you guys air kerma last time. This is very similar, and it has been. I showed you coulomb per kilogram, so you can know how much charge, right, and what amount of air we're measuring, right? We're measuring a kilogram of air, but we've replaced coulomb per kilogram largely with this unit called air kerma. Okay? Kerma just stands for kinetic energy released per mass unit. Kerma, kinetic energy released per mass. So it's largely replacing the quantity for exposure, and it's used for expressing the intensity of the raw X-ray beam emitted by the X-ray tube at a particular distance. Said in another way, it's measuring the concentration of X-rays at the body's surface. For that, we'll largely be using the unit called the gray. You guys have been used to the gray already. You saw the gray used last time. I told you things like 1 gray of X-rays to the whole body has the potential to cause death, right? So you learned that last time. So we use this unit called the gray. When we do this and use the unit called the gray to talk about entrance skin exposure, we'll have to be specific because we also use the gray for absorbed dose. So next to the Y, we put a little subscript of A for air, and you'll see that used later on. And when we're talking about tissue dose, we put a little subscript of T for tissue next to the Y in gray. But for right now, the gray is the unit. Okay. So the next one we're going to get to talk about is absorbed dose. Okay. So things to remember when we move from talking about exposure in the air to talking about actually what has been absorbed into the body. Absorbed dose says that some of the radiation that you were exposed to will pass through you, will penetrate through the body. Okay, so some of that penetrates through the body. The absorbed dose, because some of the X-rays penetrate the body, is expected to be slightly less than the surface exposure is. Measurements taken have shown that 1 gray of air kerma will come out to about 0.96 grays of tissue dose. That means whatever the exposure in the air is, the actual absorbed dose is a little bit less. It's 96% of what the air exposure was. Okay. However, 96% is pretty close to 100%. So for the purposes of just keeping things easy to understand, we often just say 1 gray of air kerma, 1 gray of exposure, entrance skin exposure, would equal 1 gray in tissue dose. They are a 1-to-1 unit. Okay, they don't have any conversion units. They just one equals the other. Okay, they're equivalent. Okay. So right now we've learned 2 things. We've learned that we measure entrance skin exposure. We like nowadays to use the gray as our unit, and we also use that same unit for absorbed dose. In all actuality, entrance skin exposure and absorbed dose are a little bit different. There's always a little bit less absorbed than entered the body, but because they're very close, we just give them a 1-to-1 relationship. We say that one equals the other. Okay? We say whatever the entrance skin exposure is, for our purposes, that's what you had absorbed. Just makes it easier because, again, they're very close to each other. Okay, so I've given you entrance skin exposure measured in gray. I've given you absorbed dose measured in gray. The next one we're going to learn about, and you guys have already heard it, is called the sievert. Okay, these are again, remember, these are the SI units. These are the international units of radiation measurement, and you won't need to necessarily remember the older British style measurements that I gave you last time. So yeah, the gray is technically a physics unit. What do they mean by that? It's a physics unit. What is physics? Like, what is the broad category of physics? You guys are going to take a physics module. We're going to learn about energy and how things move. Okay, that's what physics deals with. It deals with movement and energy. Okay, so the gray that we use for entrance skin exposure and absorbed dose is a physics unit. It's telling you you had this much energy in your X-ray beam. That's how much it's, and the amount of energy in the beam is proportional to how many ionization events, right? What is ionization except for movement and energy transfer, right? That's what an ionization event is. It's an atom is struck by an electromagnetic wave, okay? That wave simply carried energy. Then it deposits its energy by moving into the atom, and the atom's electrons become energized, and maybe one of them is ejected. Okay, it moved, it gained energy and moved, so it's energy and movement. The gray can only tell you about energy and movement. It can only tell you about energy transfer. The gray cannot tell you how harmful something is. It can tell you this is how much of it there is, but it can't infer how much harm it's caused, because we need to also know the type of radiation we're dealing with. As you learned last time, because I wanted to preempt you for this, alpha radiation, alpha particles, which are those big, massive helium nuclei, they're 20 times more harmful than X-rays are. In fact, we measure other types of radiation harmfulness against X-rays. So it's not hard. All you need to know is the gray. So if I tell you what the tissue dose was, and I tell you the type of radiation, using this next table that I'm going to give you, you can tell me what the sievert dose is, what the actual effective, what the equivalent dose is. Okay. All right. So to derive sieverts from the gray unit, the dose is multiplied by something called a radiation weighting factor, or W subscript R. W sub R is the relative harmfulness of the type of radiation that you were exposed to and absorbed into you compared to X-rays. Okay, so if we're comparing everything to X-rays, what would be the radiation weighting factor for X-rays? Are X-rays more harmful than X-rays? They're the same, right? So if you're comparing X-rays to X-rays, there would be a relationship of 1 to 1. The ratio is 1 to 1. They're the same, right? X-rays are given a radiation weighting factor of 1 because we're comparing everything against them, okay? So if I tell you, right, if I tell you the patient gets 1 gray, right, 1 gray of X-rays versus 1 gray of, let's say, alpha radiation, okay, that's the same. Their absorbed dose, I'm going to put a little subscript of T here, their absorbed dose, well, you tell me, are their absorbed doses the same? Yes, the absorbed doses are exactly the same. Gray is the unit for absorbed dose, right? We just said that, right? Gray is the unit for absorbed dose. So If I give you 1 gray of X-rays and 1 gray of alpha particles, is the absorbed dose the same? Yes. Okay, good. But dose equivalent is given in the unit called the sievert, right? The sievert. To determine dose equivalent, which talks about biologic harm, you also need to take into account the type of radiation. So while the absorbed dose could be the same between two types of radiation, the amount of harm is not the same, okay? So this table here shows you the radiation weighting factors for the different types of radiation. So what you'll do is, you'll take, I'm going to put it down here, you'll take the gray and you'll multiply it by the radiation weighting factor. So what's the radiation weighting factor for X-rays? Okay, so you would take 1 gray, multiply it by 1, right? Because the radiation weighting factor for X-rays is 1. And that would tell you in sieverts, that patient got 1 sievert of dose equivalent who got the 1 gray of X-rays, okay? But this next person who's standing next to this, this fortunate person, the unfortunate person here, they got 1 gray of absorbed dose, right? But they got it not from X-rays, they got it from alpha particles, okay? What's the radiation weighting factor for alpha? 20. So instead of a 1, they get a 20 there. So what's their dose going to be in sieverts? And what is the sievert indicating? What's it telling you about?
Radiation exposure?
Not exposure.
The absorbed dose?
Not absorbed dose. So we learned that the gray measures exposure, and the gray also measures absorbed dose, right? But the sievert measures something different. What are we measuring right now? The amount of harm, right? The sievert tells you how much harm is caused by a certain amount of absorbed dose, okay? Again, you can get 1 gray of X-rays or 1 gray of alpha radiation, and you absorbed the same amount of radiation, okay? But importantly, alpha radiation has a radiation weighting factor of 20, where X-rays has a radiation weighting factor of 1. So what's that telling me? Yes, and how much more harmful? 20 times more harmful, okay? Because when we do the small equation here, we see that we get 1 sievert of dose equivalent from 1 gray of X-rays, but we get 20 sieverts of dose equivalent from 1 gray of alpha radiation. So when you see the unit, the sievert, that's telling you how much harm is caused, okay? So again, you could receive 2 patients, right? Patient number 1 and patient number 2, right? They both receive the same amount. They were exposed to the same amount, and they absorbed the same amount, but their sources were different, okay? Patient 1 got X-rays, patient 2 got alpha radiation. Patient 2 got 20 times more biologic harm from the alpha radiation than the patient who got the X-rays. Okay? So you could receive the same dose, but you could be wildly different in the amount of biologic harm because the 2 sources of radiation were different. Okay? X-rays and gamma rays have a radiation weighting factor of 1. Beta radiation has a weighting factor of 1. Fast neutrons have a radiation weighting factor anywhere from 5 to 20, depending on how fast they're traveling. Neutrons and all atomic particles, protons, neutrons, electrons, all have the same mass. Like you take a neutron from over here and you go over, fly to Australia and you go pick up a neutron. You're not going to, but you get the point, right? You pick up a neutron in Australia, they're going to weigh the same. They have the same mass. So masses don't change. What changes with the amount of harm here, why it's anywhere from 5 to 20, is because some neutrons can be emitted very slowly, others can be emitted very quickly, and the amount of damage they cause varies based on their velocity. And alpha particles are the most harmful at 20. Why are alpha particles the most harmful? What did you learn about alpha particles last time?
That they can't penetrate very easily.
So they don't penetrate, so that's bad, right? What are alpha particles? Close. Helium. They're a helium nucleus. Okay, 2 protons, 2 neutrons. They have an atomic mass of 4. Right? They're 4 things. Right? Their atomic mass unit is 4, and they have a charge of +2. They're charged and they're very large. Okay, charged and they are massive. Okay, so for that reason, being charged and massive, they're very harmful because they don't penetrate very far. That's why their radiation weighting factor is so high at 20. Again, important thing here to remember is you can know what the exposure is, you can know what the dose is, but if you don't know the type of radiation, you cannot infer an amount of biologic harm. Okay, that said, we need to remember, so we need to be able to simplify things, right? Because in X-ray, in the X-ray field, what type of radiation are we dealing with the most or exclusively? There's alpha, beta, gamma, X-rays. What type of radiation are we dealing with exclusively? X-rays. Do we deal at all with alpha, beta, and gamma radiation? No, right? So while we learn what the radiation weighting factors are for other types of radiation, the most important thing for you to remember is that we deal with X-rays, okay? That's what we're working with, okay? Yeah.
Is there any way that we can ever be around any of the other types of
Yes,
X-rays?
definitely.
I mean, X-rays of the other types?
We are right now.
Yeah.
Yes.
How's that?
5,000 times per second. Your body, minute, 5,000 times per minute. Your body, RV's body, Chloe's body, my body, right? We are all about 5,000 times per minute having radioactive decay events because we all have small amounts of things like potassium, uranium, and so forth. So these alpha, beta, and gamma emissions are happening in your own body all the time.
Aside from our own body.
Yes, cosmic radiation, terrestrial radiation. So if you want to be, I'm poking at you because I want you to be specific. Aside from the natural background radiation, no. Yeah, so there are no abnormal sources of particulate radiation. It's all going to be, you're going to be exposed to it, but it's from the natural background, internal, terrestrial, all those normal sources that we talked about last time. There are not going to be any surprise sources of alpha, beta, or gamma. Yep. That's a good question, right? Because and to be exposed to those things, you have to be around a radioactive source, and we have some of those elements in our own bodies and in our soil and in our, in this glossy stuff on the magazine has a little bit of uranium in it, but otherwise no. Good. You can go find, if you go antique shopping and bring a UV light with you, you can go find uranium glassware. That still exists. It glows bright green when you expose UV light to it. So you can find some radioactive stuff to be around, right? But not necessarily, and not in your own course of work.
Could that cause heart death?
Yeah, small amount, not necessarily. No, it's not radioactive enough to be like super harmful, but it exists. It's out there. Yeah. Good. So my whole point here is that because we work with X-rays, and X-rays have a radiation weighting factor of 1, because the whole idea is comparing the harm of a type of radiation compared to X-rays. Well, comparing X-rays to X-rays is like comparing apples to apples, right? An apple versus an apple are the same type of thing, right? No, one is not more apple-y than the other, okay? So for X-ray purposes, as shown here, 1 gray of X-rays equals 1 sievert of X-rays. For X-rays, the radiation weighting factor is 1, so the absorbed dose is equal to the amount of biologic harm. Okay? There is no more that you gain once you know that we're dealing with x-rays. You don't gain any knowledge by knowing the dose equivalent versus the absorbed dose. You just have to be able to differentiate those two things, what they actually mean, okay? But if I tell you the patient got 1 gray of x-rays, you know they got 1 sievert of biologic harm, and it's a one-to-one relationship. So 1 gray of air kerma equals 1 gray of absorbed dose. We knew that already. And in x-rays, 1 gray of absorbed dose equals 1 sievert in dose equivalent units. Okay, so there's a one-to-one relationship. The gray equals the gray equals the sievert. And it is that easy for x-rays.